I drew a few functions on the board here, and all of these functions have some place where they're not differentiable, some place where I cannot find the derivative. The term differentiability is really just saying, where can I find the derivative? Where can I find the derivative of this function? So as you can see in this first case, it looks like I can find the derivative. Remember, a derivative is just a slope. I can certainly figure out what the slope is at all these places. I mean, some kind of positive slope. But all of a sudden, I get to this corner. What's the slope of a corner? I mean, how could you figure that out? Is it like on this side or this side? I mean, really, it's like a very sharp point there. You can't measure the slope at a sharp point. So this function has a point that is non-differentiable right here because, what should I write there? Sharp corner? How about that? Sharp corner. What do you think, Ms. Stewart?
Looks fabulous.
Terrific. So that's a point where it's not differentiable. There's no derivative there. There's another function that has a point where you cannot take the derivative. And you want to tell me where that is, Ms. Stewart?
Well, I think it's going to be kind of right in the middle of the function there.
That is exactly right.
It looks like if you find the slope, it's going to be, yeah, no slope.
Right. I mean, the slope is getting steeper and steeper and steeper and steeper, and all of a sudden, it's straight up and down. And of course, you know when a slope is straight up and down, when a function is straight up and down like that, you say the slope is undefined. You can't measure that slope. It's infinitely steep. So I'm going to say this is a point of non-differentiability because the function is vertical at this point, or I'll say undefined slope. Got two more. There's another function. Obviously, I can't find the derivative right here. This is probably some kind of piecewise function where there's a jump. Well, right where that jump is occurring, how do I measure the slope? I mean, down here, I'm kind of at this end point. Is it like on this side or that side? It's another. It's kind of a sort of a corner type of situation. So there is no derivative there. It's non-differentiable because the function is not continuous at that point. And here's another piecewise function, and it's really the sharp corner case again, but you can see the two pieces of the piecewise function are meeting at this point right here, but they have different slopes. So, I mean, I could say sharp corner, or I could just say as the two pieces meet in a piecewise function, they have different slopes than each other. And those are the basic cases of non-differentiability.
So how do we determine if a function is differentiable at a point if we're not looking at the graph? Well, we can try to do it algebraically. Here's a function, f of x equals fx to the 1/5 plus x. The question is this differentiable at x equals 0? When we're asking if it's differentiable, we're asking, can you find the derivative of this function when x equals 0? So let's take the derivative and see if it exists when x equals 0. That seems reasonable. So the derivative of this function, I'm going to use the power rule. 1/5 times 5 is 1. X to the 1/5 minus 1 is -4/5 plus 1. So that's the derivative of this function for any x. I want to see if the derivative exists when x equals 0. So you know what I want to do before I do that maybe is just rewrite this so I don't have a negative exponent. Sometimes it's easier for me to really see what's going on if I don't have that negative exponent. So of course the negative exponent puts this down in the denominator. That plus 1 is okay. So let's see if this derivative exists when x equals 0, shall we? We'll plug in 0. Oh my gosh! I'm afraid to write it in case the math police come busting in that door because what am I doing? What am I doing, Mr. Haas? Or trying to do?
I think you're trying to divide by 0.
I'm trying to divide by 0. We know that that's nonsense. That doesn't make any sense. That doesn't work. Therefore, the derivative does not exist when x equals 0, which means that this function is non-differentiable at x equals 0. So I'd actually say that it's non-differentiable, this function, at x equals 0.
Now, if you put in like another x value, could it be differentiable there?
Well, I
Like if you
imagine,
put in like 1 or something like
Could
that?
I put in 1 here?
Would that
1
work?
divided by 1 to the 4/5, I'm pretty sure that's just 1. 1 divided by 1 is 1. 1 plus 1 is 2. Sure, when
Oh,
x is
okay.
1, my slope of this function
But
is 2.
at 0, there's no
At
derivative.
0, there's no
It's
derivative.
non-differentiable, no derivative.
Non-differentiable at x equals 0.
I think I get it.
Good. Should we try another example? Let's try another example. Again, the question, is this function differentiable at x equals 0? Does the derivative exist for this function when x equals 0? Let's take the derivative to find out. So here I go. Again, I'm going to do the power rule. 2 times 4/3 is 8/3 times x, subtracting 1 to the 1/3, minus 7. So there's the derivative of that function. To see if it's differentiable at x equals 0, I want to plug in 0 into my derivative to see if the derivative exists. All right, how am I doing so far, Haas?
Looks good.
All right, I'm just going to be substituting in that 0. Any problems here? I don't think so. 0 to the 1/3, it's like the cube root of 0 is 0, times 8/3 is 0, minus 7. Oh, heck. My slope is -7 when x equals 0. My derivative exists. So this function is differentiable at x equals 0. I would answer this question with a resounding yes. It's differentiable at x equals 0.
So I noticed you used x equals 0 again for this problem. Are functions only not differentiable at x equals 0?
You
or?
know, I'm so glad you asked that. The reason we're using x equals 0 is because we want to work with functions that you know how to take the derivative of.
Yeah.
Down the pike a little bit, we will be working with a little more complex functions, and then you will see that it's non-differentiable at other places.
Got it.
That's
Thanks.
why the x equals 0 shows up a lot.
Thanks, Stuart.
Thanks, Haas.